So thank you very much, Olivier, for the introduction. So hello, everyone. So my name is Iain Henderson. I'm a lecturer in applied mathematics at ISAE Supaero in Toulouse. And today I will be talking about physics-informed Gaussian processes. Right, so let me just check this. Right, so here's the outline of the talk. So I'll start with an introduction, general one. And then I'll talk about, and also a bit on partial differential equations, which are the typical mathematical models that people encounter to model physics. And then I'll talk about how we can combine the theory of partial differential equations and Gaussian processes. I'll just set my timer so that I don't mess up the schedule. Right. I'll provide some examples, and then I'll show you an application, sort of a real life, quote unquote, with the three-dimensional wave equation, which is important in acoustics, for example. So I'll talk about my PhD work, which is starting to be a bit old in some sense. So my advisor was actually Olivier Rostand and also Pascal Noble. So they have very different areas of expertise. So Olivier comes from the machine learning and uncertainty quantification community, whereas Pascal was from the PDE theory and fluid mechanics. Right. So first of all, Gaussian processes. So what is it in a nutshell? So it's if you come from the machine learning community, you would call that a kernel method. The only difference is that I'm going to introduce it with a probabilistic point of view, and it's used for doing many things. For example, for doing statistical learning. So that's the first example. Right. Whoops. Yeah, I'm. Right. Surrogate modeling, which is an application of machine learning. So where the goal is you want to emulate a costly black box function, and you only have a limited data set. Also, one of the main perks is that it provides uncertainty quantification. So it provides a predictor, but you also have uncertainty bounds on the predictor, so which is very interesting for real-life problems. And also, it's interesting for solving inverse problems. And actually, with Jérôme at the moment, we are working on data assimilation problems using this kind of technology. Right, so what am I going to do today? Then, well, so I'll motivate the use of Gaussian processes for solving PD problems. I'll focus not too much, but still, on the mathematical aspects of doing this, and then I'll provide you a small recipe on how you can combine PDEs and Gaussian processes. And then, as I said, I'll provide an application. So the question. So I don't know if the Régie is able to press the play buttons. If that's not possible, then I'll. Right? Yes. Perfect. So on the left-hand side. Oh yeah. So but perhaps your. I think you need Adobe Reader. Okay. So I think we'll just skip this. So what you're supposed to see on the left-hand side of the slide is a numerical simulation of a wave propagating, right? And assume now that you only have point-wise measurements of this phenomenon, okay? But you know two things. So first of all, you have the data, but you also know that your observations are constrained by some physical principle. And here it's going to be the propagation of waves. And if you combine those two things correctly, on the right-hand side, you'd be supposed, well, in theory, because you have to believe me now, to see that you can actually have a really nice reconstruction with not too many data points. And how do we do that? Well, in a nutshell, you impose the physical constraints on your machine learning model. Right. So I'll provide a few slides on what are Gaussian processes. And how do people use it to do to solve regression problems, typically? So, what's a Gaussian process? Well, a Gaussian process is a random process. So it's a collection of random variables, which is simply going to be indexed by some set. Okay. So it's nothing more than just a collection of random variables. If you have that, you have what you would call a random function, right? So where you fix. You fix the sample omega, right? And you end up with a function, okay? So that's a stochastic process, and it's the basic model for random functions. And among all of these models, you have Gaussian processes, which is a very important and a nice class to manipulate, to do math with this. So I've provided you the definition here, but in a nutshell, the Gaussian process is basically a Gaussian distribution, but over spaces of functions. And how do you use this in practice? Well, you only have to manipulate two things. First of all, the mean function, which is, whoops, yeah, sorry, I'm getting used to this. This function, right? And then you have the covariance function, which is the covariance between these two random variables. Okay? And then I'll simply denote it like this. Okay. So maybe you've heard of the Brownian motion, which is the most famous Gaussian process. So here I've shown you different realizations of the Brownian motion. Okay? So I've taken different samples, and then I can have a numerical simulation of different samples. And here are the associated mean and kernel functions. Right. Oh yeah, so by the way, this covariance function is going to be the so-called kernel in this kernel method. Okay, so let's look at the properties of this mean and kernel function. So the mean can be basically any function, and typically people just set it to be 0, and then we just forget about it. The kernel, the covariance function, or kernel, has to have two very important properties. So first of all, it has to be symmetric, okay? But it also has to be a positive semi-definite function, which I'm going to shorten as a PSD. So what does this mean? Well, just as for a Gaussian distribution, the covariance matrix has to be a positive semi-definite matrix, then this also has to be true at the level of the covariance function. So how do you write this? Then, well, just consider the matrix with entries like this. So it's square. And whatever these points, this matrix has to be positive semi-definite. So it's easy to see that you have to have this constraint. It's not obvious that it's also true in the other way around, meaning that if you have a symmetric PSD function, then it is the covariance function of some Gaussian process. This means that in practice, to manipulate Gaussian processes, we'll only need to use this function k. Okay? And in particular, if you're interested in plugging in given properties on your Gaussian process, you're going to do it on the kernel function. Okay. So how do people use this to solve regression problems? Well, so as I said, typically you have some unknown function. You also have a finite set of pointwise observations. And what people typically do is say, okay, I don't know what my function is, so I'm going to assume that it's some realization of some random variable, which here is going to be a Gaussian process. So in Bayesian terms, I'm going to say that I'm going to put a prior distribution on U, okay, which is going to be just some prior Gaussian process. The nice thing with probability distributions and priors and things like that is that you can update them, right? How do you update it? Well, simply you use Bayes' formula to just condition your distribution on your data. If you do this, you have a condition process, so a new Gaussian process with a new mean and new covariance function, which are the updated, which is the posterior Gaussian process, so the updated process. And how do you do estimation with this? Well, your estimation is simply going to be the posterior expectation, okay? It's what you expect to be the most likely given your data, basically, in a Gaussian setting. And you also have a measurement of uncertainty, which is going to be the posterior variance. Right. So just an illustration of how this would go in practice. So this is my black box function. I'm only allowed to use pointwise values. And if I do Gaussian process regression, so what I've just described, this is the kind of thing you would end up with, right? So you see in blue, you have the posterior expectation, okay, which is going to be your predictor, but you also have uncertainty bounds, okay, which are the expectation plus or minus 2 times the posterior expectation. And I've also drawn you samples of the conditioned Gaussian process. Right. So this is how things look in practice. But now you see that you have a lot of room Okay, so you can do, there's a lot of things you can do if you choose well your kernel function. So for example, you can impose prior regularity assumptions, okay? So let's assume, okay, my function is at least continuous, or C1 or Cn, okay? Well, this is some property then that you would then want to impose on your prior distribution, okay? Because this is a priori knowledge, right? How do you do this? Well, you have, so it's well known in the literature, but you have conditions on the kernel, okay? So regularity of the kernel implies regularity on the covariance function, okay? More interesting in the context of this talk, what if you know some linear invariances? For example, you know that it's symmetric, or it's an even function, or an uneven function, or things like that. Or if it has some rotation invariance. Well, you can show that, so typically you want to impose this invariance at the level of your random field. There's a condition, which is this one. If you're able to impose this, then you can show that you end up with this condition. Okay? In particular, all your estimators will have your desired properties. Okay? So I've written a small sketch of proof, but I think I'm just going to skip this. Yeah, anyway. So the main message is that by constraining your kernel function, you end up constraining your Gaussian process. And actually, what I'm going to do, I'm going to spoil my talk. I'm going to this L invariance is going to be a PD. Whoops, right? It's going to be a PD. So just an example. So for example, here I've chosen a periodic kernel function. You can see that the samples are always periodic. They're random, but they're periodic. And also, they're a bit more. You can see that they're almost. So if you translate them by 1/2, you would end up with even functions. Okay, so you can see that you can impose things on your prior distribution. Right. So that's for Gaussian process modeling. Now, what about PDEs? So what could be the main idea here? So as I said, if you want to take into account prior knowledge, then you have to do it by choosing the kernel K accordingly. Okay. By doing this, you actually only focus on relevant function space. So you want this H space to be, let's say, as small as possible, but while remaining relevant. So what I'm describing here by choosing a good prior is actually some sort of a dimension reduction procedure. Right. So what will be my general problem here? I have a database of observations, some unknown function, and my function is going to be constrained by physics. Okay, so this is going to be a differential operator. And I'm going to try to impose my PD on my prior distribution. So just an example, just so you have images, and actually this is not a video, so you can actually see things. Right, so I'm going to focus on a very simple equation, which is the heat equation. Okay, so one dimension in space, and you have some initial data. And let's say that you have some sensors on your rod, okay, where heat is propagating, and you only have these measurements available. Okay, so you want to try to approximate the full space solution by combining this and your knowledge of the PD. Okay, I know that this is some heat temperature, so I know that it follows the heat equation. So you're going to look for a kernel that verifies this, where L is going to be your differential operator. Okay. And actually, if you do this, you can actually do this. I'll give you a formula later on. But this is the kind of thing you can end up having. That's the real solution. That's a Gaussian process prediction with some general kernel where you don't put any physics. So you can see here that for example, the approximation has absolutely no idea that actually your solution is going to have to go to 0 in some sense, because it's just heat diffusing. Okay. So you have a lot of uncertainty. Whereas if you put physics, then you're going to know your approximation model knows that you're facing a diffusion problem. Right. So now on a quick note, I'm going to try not to be too long on this, but the heat equation is a very nice equation. Solutions are always regular, and life is beautiful. For some PDEs, for example, a very simple one, the transport equation, which simply describes the transport of some quantity at speed c. For some PDEs, the solutions have no reason to be smooth, right? Because if you solve this, you might have done this at some point in your past life. You can prove that the solution is the initial condition just translated at speed c. Okay, so it moves at speed c. But you can see that if this is rough, then your solution has no reason to be rough. And actually, that's the problem that occurs very, very often in PD theory. Okay, so the question being, in what sense can we say that this is a solution of this when your initial data is rough? Okay, so solutions of partial differential equations that you can't differentiate. That's weird. Okay, so this is well known. So you might have heard of weak formulations. Okay, where you basically, so it's some sort of trick where you're able to say that this is a solution of this. Okay, yeah, this. Sorry, and the weakest of all is the distributional formulation. Okay. So I'm just going to stop there, but that's just to say that there's this problem that's very important in PD theory, and it would be interesting to be able to combine, or let's say, combine this way of phrasing things that people are very, very good at in the PD community and try to impose it on our machine learning problem. Because you can see that typically assuming that your solution is smooth is not something you're going to do, you're going to want to do in this case. Right. Now for some theory, and then I'll provide you some examples. Right, I have a random field. I'm going to use it as my prior distribution, okay, on my regression problem. So if I know that my solution verifies my PD, I'm going to try to impose the PD on my prior distribution, which is phrased as this. The question is, how do I do this? So this is a theorem simplified. I have a differential operator, so I don't have to assume that it has a constant coefficient. I have to assume that it's linear, though. Okay. I'm considering a random process which has a covariance function. Well, we were able to prove in this paper that imposing this, so remember this is exactly the criterion that had already appeared earlier on. Okay. If you impose this on the samples, on these functions, then actually this is equivalent to imposing your PD on all the samples. So this is exactly what we want. Okay. So this tells us how we have to design our Gaussian process. And actually, in our paper, we were able to encompass the distributional sense, meaning that our non-smooth solution is also taken into account. So we are able to deal with this case with our theorem. Right, so now for some examples. Right, so let's go back to this weird one. Okay, so very simple, the transport equation, but with non-smooth solution. So we want to impose this thing. Okay, so let's you're looking at a solution of a transport phenomenon. So you want to impose the transport equation on your prior. And the question is, how does the kernel look like? Well, you can show that your kernel has to be of this form. Okay, where K0 is some given covariance kernel. Okay. A quick comment. You can see here. You can see that we recover the structure that of the general solution. And a quick comment. So, for example, if you take a non-smooth kernel, okay, so this is continuous but not differentiable, then this is going to be continuous, non-differentiable, but still the samples are going to be a solution of this transport phenomenon. Right. A bit more complicated now, well, in terms of the formulas, but not really in terms of maths. Let's go back to the heat equation. Okay, so the example that I had given you before. Actually, you can come up with some So it looks it looks like it comes from some place where, so I'm going to tell you where it comes from actually. But you have this Gaussian distribution where you have this coefficient here, okay? And if you select this as your covariance kernel, then your samples are going to verify your PDE. Okay? So where does this come from? So you might have heard of the heat kernel. Okay? So it's the heat kernel. So it's just the density of this Gaussian distribution with variance t. So it flattens out as t advances. Okay. It's not obvious at all that this function is PSD in the tx variable. Okay. And now I'll tell you where this comes from. And so I'll try to be quick, and then I'll describe the application. So how do you build such physics-informed kernels? So I'm going to have some assumptions here. I'm going to assume that my PD is linear. It's going to have constant coefficients. And I'm going to assume that it's full space, so no boundary problems. So I'm just going to consider some general linear partial differential operator. So don't worry about it. It's just a notation for some partial differential operator. And if you've ever heard of impulse responses in control theory or in signal processing, well, this is exactly what I'm going to do, but at the PDE level. So in the PDE community, this is called the Green's function. Okay, but it's exactly the same thing. I look at my PDE, and I put an impulse at the origin, and I just propagate it. That's my impulse response, G. And the theorem is that your solution is given by the convolution of your impulse response with your data. Okay? And this is very common in control theory or signal processing. So just a quick reminder of what is a convolution. Right. And now let's mix Gaussian processes with this. Okay. Let's assume that my initial Gaussian process, sorry, my initial condition is a Gaussian process. Then my solution has to have this form, and then I can just compute this convolution, and then I can wonder what's the covariance of this thing. I just write it out. So it looks complicated, but it's just switching integrals. So I think you've done this at some point in your life. You just switch integrals, and you end up with this general formula. And actually, in my two previous examples, this is exactly the shape of the solution. Okay, so if you're interested in the recipe, if you have some linear PDE, you can just use this, and this will give you a physics-informed kernel. Right. Okay. Also, you can see that in red, there's C and D. These are physical parameters, and they end up being parameters of your covariance function. In Gaussian process regression, there's a bunch of ways on how to tune the parameters. So by using these methods, you can actually tune the physical parameters, so do physical parameter estimation. Right. So just to go back on my solution. So it's the exact same slide, but here I've used the formula that I had given you. Right, and here's just a bunch of physics-informed kernels if you're interested in some of these equations. Right, and right now I'm going to focus on the 3D wave equation. Okay? But all of these are very important and standard linear PDEs where you have Green's functions and then you can compute physics-informed kernels. Right. So now for the application. Okay. So acoustics. So what is this? This is the wave equation. So this is the three-dimensional Laplace operator. Right. This is the wave equation. So it's exactly the equation that dictates the propagation of acoustic waves. Okay. So the sound that you hear is given by this equation. Okay. So I'm going to store this, all of this linear differential operator. I'm going to store this in this square, which is called the D'Alembert operator. And this is a second-order PDE. So I have an initial position, right, and an initial speed. Okay. So when you have a second-order time derivatives, you need information of the position and speed. So time derivative at 0. And I'm going to do exactly what I've done in the previous examples, which is just use the formula that people use in acoustics, which is called the Kirchhoff formula. Okay. So I'm going to have some Green's function, ft and ft dot. Okay. So what is ft? This is a constant, And this is, so sigma means that it's the Lebesgue measure. So this is actually a measure. It's the Lebesgue measure on the sphere of radius ct. Okay? And then you end up with this spherical average formula. How do I build a kernel with this? Well, I assume that V0 and U0 are Gaussian processes, and then I end up with this scary formula in some sense, but you can compute this. Okay? And this is the general form. Your kernel has to have this form if you're interested in the wave equation. Right? So what can I do with this kernel? Okay, because these are models, but now I'm gonna show you some practical applications. So if I look at my Gaussian process regression estimator, it's also gonna verify my constraint. Okay. In particular, if I evaluate this thing at t is equal to 0, I can estimate my initial data. And actually, estimating the initial data of the wave equation is a well-known problem, which is called the photoacoustic tomography. Okay. Right, so this is what I'm going to do in the next slides. And as I said, you can also estimate physical parameters and things like that using a method called marginal likelihood estimation. Right. And I'm going to skip this comment. So for the example, and then I'm going to conclude. So this is my initial data. So we are in 3 dimensions, right? So this is a slice, okay? This is a fixed z and x and y. Okay? This is my initial data, and then I have scattered sensors in my numerical simulation. Okay? So here I assume that. So my initial data has a spherical symmetry. My sensors, they pick up some signal, and then I'm going to use my kernel to estimate my initial data using my method. So that's the correct U0, and this is the estimation we were able to obtain in our paper. Okay, so it's quite good actually. And also the position of the source was also unknown, so it was estimated via Gaussian process regression tuning. Okay, so the fact that it's centered, it's something that we were able to recover from the data, okay, using Gaussian process regression. Right. And now it's time for my conclusion. So I've given you, I've told you about how we constrain Gaussian processes with PDEs, which may be rough. I've given you a theorem. I've given you a recipe. It may be also relevant to focus on interesting energy spaces. So I haven't talked about it here, but if you're interested in PDEs at some point, this is a problem you're going to have to encounter, right? And I've given you an application on the wave equation and solving related inverse problems. At the moment, we're working with Jérôme on bathymetry or bathymetry inversion using these kernel methods, right? And using our theorem. And at the moment, we're also working on Gaussian process regression with Deborah, Jérémy, and Olivier on high-dimensional Gaussian process regression problems. And I'll just skip on this. So thank you all for your attention, and I'm waiting for your questions.
Many thanks, Iain. We have time for one brief question.
Thank you for your nice presentation. A question, have you, because what you are assuming that the medium is homogeneous or isotropic. The question is, have you thought to extend your method when you have, for instance, 2 types of media with an interface where the
not for the wave equation, but actually at the moment with Jérôme, we're working on we have a linear PD with non-constant coefficients, which is basically your case, right? And we're trying to split the domain where we're gonna assume that the coefficients are locally constant. Okay, so P0 approximation, and then so you have Green's functions, and then you can condition them to be to have a continuity at the interface, right, using Gaussian process conditioning. And this is actually something we're doing at the moment.
Thank you.
Thank you very much, Iain. For time reason,
Thank
we
you.
go to the second talk.